All right, so current electricity. So electricity is basically electrons moving through a wire. So the electrons, they're going to be either moving or flowing. We like to say they flow. So electrons flowing through a wire, and then they can do work. So you remember that work is a force working through a distance. So the electrons push through the wire with a force over a specific distance, and they're able to do work with that. Okay, so that's all that means. Current is denoted by an uppercase I, and the unit that we use for current, I know the C is cut off, sorry, current is the unit that we use is amps. AMPS or amperes is what you would say, the whole long word. Nobody says that, they just say amps. Okay, and this is the number of electrons passing a point per second. Okay, so we like to say it's the rate of flow of electrons. So you can almost think about it as like the velocity of the electrons, like how fast they're moving through the wire. Okay. Voltage is denoted by an uppercase V. The unit for that is volts. Voltage is in volts. And we like to call this the potential difference. Okay, potential difference. So anytime you see the words or hear the words potential difference, that means voltage. Okay, how many volts? All right, so what is that? This is the amount of push on the electrons. Okay, so think of that as a force. So voltage is the force applied to push the electrons. Current is how fast they're moving. Okay, that's basically what this is. And you already know about like distance and force and velocity. So it's the same thing, just with different words. Okay, now resistance is denoted by an uppercase R. The unit is an ohm. Okay, so the unit is in ohms. Ohms has a symbol also. Okay, so an ohm is actually an omega symbol. Okay, that's an ohm. Resistance is in the name, okay, is the opposition to flow of the electrons. Okay, so this is dependent on the type of material cross-sectional area, length of wire, and temperature of wire. Okay, so the wires that offer the least amount of resistance, okay, with regards to these types of conditions, okay, so least resistant wires are short, fat, and cold. And obviously made of metal. Okay? So that's how you want your wires. You want your wires short, fat, and cold. If they have to travel long distances, it takes longer. Okay, so you won't have as great a current probably. So cross-sectional, if it's a thin wire, you won't be able to push as many electrons through it at one time. So, all right. All right. All right, so a resistor is an electrical device. Device. I think it's spelled device. Device that makes it harder for the electrons to flow. Okay, a voltmeter measures potential difference. I don't know why that line is so small, but anyway, potential difference between 2 points in a circuit. And you have to place it in parallel with the circuit. An ammeter measures current, and that's placed in series. Okay, so your circuit symbols for a resistor looks like a squiggly line in the middle of like a straight line. That's really it. Okay. A voltmeter, you'll have like a circle with a V in it that's going across your line. An ammeter, circle with an A in it going across a line. The battery, short, long, that's a battery. A wire is just a line. A bulb looks like a circle with like a kind of like a curly lowercase L in the middle, like a curl like that, in the middle of a line. Bulbs and resistors do the same thing, so they're kind of interchangeable. If you want to use bulbs, you can use bulbs. If you'd rather use resistors, you can use resistors. When you're drawing your circuits, it doesn't matter. And a switch, if it's open, it looks like that. If it's a closed switch, it'll be a line with 2 dots to show that it's been closed. If it's closed, that means the circuit is connected. If it's open, that means the circuit is disconnected. Okay? Okay, and then we get to Ohm's law. Okay, so Ohm's law is kind of easy. And this is mostly what we're going to do today when you do your activity. So Ohm's law. So for a given resistance, the potential difference is I don't want to just say proportional. The equation is V equals IR. So the potential difference is directly proportional to the current. So as voltage increases, current increases for a specific resistance. That's what directly proportional means. Okay? All right. So, and that's the equation V equals IR, where V is volts, I is current, R is resistance. So volts equals amps times ohms. Okay? All right. We're not going to draw the circuits just, well, we could. It's not going to kill us. You have a 12-volt battery connected to a light bulb. 6 amps flow through an ammeter. Find the resistance of the bulb. Bless you. So if we have let's just connect the battery to a bulb. So that's just called a simple circuit. So there's my battery, and it doesn't matter which way you draw it. Like if you draw it like this, or it doesn't matter. And I'm going to connect that to one bulb. And that's just a simple circuit. Okay, one battery, one bulb. It says that we connected an ammeter through it, and our current, okay, our current is 6 amps and our battery is 12 volts. Okay, so my V equals 12, I'm going to call it V for volts. My current equals 6, I'm going to call it A for amps. I want to find the resistance, looking for R. Okay, so I'm going to write my equation, V equals IR. If I am looking for R, I'm going to divide both sides by I. So then R is equal to V over I. This equation is in your equation sheet, so you don't ever have to memorize it. So It's 12 volts divided by 6 amps. I don't really care if you write the units or not. So 12 over 6 is what? 2. So that gives me 2 ohms. That's the resistance. Okay. Okay, next one. You have a motor connected in a circuit, draws 3 amps of current when it's running, and now we want to find the voltage on the battery. What motor? There's no resistance, so I don't know. I don't know, what do you want the motor to be running? Like a hairdryer? Fine. The motor's running a hairdryer. Okay? The hairdryer, let's say the hairdryer has a resistance of, I don't know, 12 ohms. Cool? So, motor's connected, 3 amps of current. We're looking for voltage, and we have resistance. So, we're going to draw our diagram. So we have a battery, okay? It's going to be connected to a motor. A motor, typically, we'll just use a resistor for that guy. Okay, so just do a little, like a squiggle, and then connect it to the battery. It's good enough. So V, we don't know. I is 3 amps, and R is 12 ohms. Well, V equals I times R. So you don't actually have to rearrange the equation this time. You just plug and chug. Okay, so I is 3 amps. R is 12 ohms. What's 3 times 12? 36. So you have 36 volts. 36 volt battery. That's kind of a powerful battery, huh? Okay. All right, last one. It says, when a heater which provides 12 ohms of resistance is plugged into a wall socket at 120 volts, we have 12 ohms of resistance, 120 volt wall socket. We want to know what will be the current flowing through the heater. Okay, so I'm going to assume the heater is going to act like a resistor, so I'm going to make a squiggle for that. It's not a light bulb, obviously. So I guess it is in like a hamster cage. That's kind of a heater, isn't it? So squiggle. So that's a simple circuit with a resistor from a heater. Okay. V equals 120 volts. I is what I don't know. And R is 12 ohms. So V equals IR. This time I'm looking for I. So what do we divide both sides by? So 120 volts over 12 ohms. What's 120 divided by 12? 10. So that's 10 amps. All right, so moving on. So power. So power is, it's the rate of conversion of electrical energy. And yes, I abbreviate energy NRG. I just like to do that. And I did that before I knew about the NRG Energy Company. I got that from one of my chemistry teachers in college. So, all right. So that means like from potential electrical energy. So, you know, energy can come in like a zillion different forms, right? You have like light energy and sound energy and like actual mechanical energy, kinetic energy, potential energy, okay? Chemical potential energy, electrical potential, whatever. So it's electrical potential that's being converted to do something, okay? So the power is the rate of which you convert that power to do something with it, like run a hairdryer, run your cell phone, run your calculator, things like that. To run, yes, sure. All right, so that's what power is. The formula for power, and again, it's on your formula sheet, so you never have to memorize it, okay? is P equals I times V. Okay? Now power is measured in watts. So this will be in watts. And you know that I, this is currents, that's in amps. And you know that V is voltage, so that's in volts. Okay? Okay, there are a couple of rearrangements of that on your formula sheet. I'm not going to go over that. Use them if you want, or don't use them. I don't care. Now, the problem with this is that it's in watts. The energy company that your parents or you, I don't know who pays the bills to, measures everything in kilowatts. I know, right? They measure everything in kilowatts. So, electric companies measure energy, and yes, I spelled it out, energy consumed, because you're the consumer, in kilowatt hours. So we like to call lowercase k, big W, little h. That's a kilowatt hour. Okay? So when you're calculating the cost of your energy, you have to convert your watts to kilowatts and then use another equation for that. So your cost, okay, of your total amount of power or energy consumed or whatever is power times time times the cost, meaning the rate at which you pay. So if you look on your power bill, like it'll say like how much energy costs per kilowatt hour. So let's say it's like, I don't know, maybe it's 0.0168 cents or dollars per kilowatt hour. So it's not even a whole penny per kilowatt hour. Yes?
For the abbreviation of kilowatt hours, are those all lowercase letters?
No. I said lowercase k, uppercase W, lowercase h. Yeah. So yeah, it doesn't matter. Okay. All right, so we're going to do a little example problem. Now, this is also on your formula sheet. You don't have to memorize it. It's there, okay? So let's do a little example. All right. So let's say electrical energy costs $0.75 per kilowatt hour. How much does it cost to operate a TV with a resistance of 60 ohms if 115 volts is applied over 24 hours. Now, hopefully you're not watching TV for 24 hours, but if you were, we're going to calculate how much it would cost on the energy bill, okay? So, first of all, we know that power equals I times V. Now, we need power to calculate cost, so we're going to have to calculate the power first, okay? We are given R, and we're given V, and we're given time, and we're given our rate, how much it costs per kilowatt hour, right? So, I don't have I, so I can't calculate power without I. So I'm going to have to use Ohm's law first. So V equals IR. So first I'm going to have to use that one to calculate I. So I'm going to divide both sides by R. So that's 115 volts over 60 ohms. So you get 1.92. It's close enough, right? Amps. So now I've got I, right? So now I can calculate power. All right, so now we've got our I. So now we need to find our P. So P equals I times V. All right, so now our I is 1.92 amps. Our volts is 115 volts. So 220.8 watts. But what do we need? Kilowatts. So I need to convert that to kilowatts. So I can do dimensional analysis, or I can move the decimal 3 places to the left. What's your choice? Move the decimal. All right, fine, that's fine. So that's 0.2208 kilowatts. Okay? And then I need to plug it into my cost equation. So now my cost total equals power in kilowatts, so 0.2208 kilowatts, times time, and time has to be in hours. Thankfully it is, so 24 hours, times our rate of consumption here, right, is $0.75 per kilowatt hours. Why does it have to be kilowatts and hours? Because it has to cancel with that. So you don't have to, but it's kind of nice. That way you keep up with what's where. So kilowatts cancel, hours cancel, and you're left with dollars. And so it's $3.97. So it costs almost $4 to run your TV for 24 hours.